Okay, so you wanted to dive into quantum field theory, which, by the way, we're calling QFT from now on because,
That's fair.
right?
Yeah.
Yeah. Buckle up, everybody. It's going to be a wild ride.
Yeah.
It's QFT. It's how the universe works at the smallest level. And let me tell you, it's not your high school physics class.
Right.
We're talking about particles, like popping into existence
Yeah.
and disappearing. Fields, forces. I mean,
It's all connected.
yeah, so excited to unpack this
Yeah.
with our expert today. But first, like, what even is quantum field theory?
So QFT, as we're calling it, it's this beautiful framework, right? It brings together quantum mechanics,
Okay,
special relativity,
got it.
and field theory. And it's how we describe the most fundamental building blocks of the universe. And the really cool part is how they interact, you know?
That's kind of a big deal, right?
It's a pretty big deal.
Yeah, and I just want to back up for a second because it's kind of crazy to think about this, right?
Yeah.
Like, how did this even come about? QFT.
So you've got all these brilliant minds, they're
Yeah.
trying to put these pieces together. You've got quantum mechanics explaining all this weird stuff happening at the smallest level. And then you have Einstein, right? Special relativity, space and time, like bending and warping, totally different.
Yeah, completely different.
But physicists, they're like, hold on, this has got to fit somehow, right? And that's where QFT comes in.
Yeah.
Dirac, Feynman, these guys, they pave the way, right? It's an incredible story.
It's amazing. And, I'm going to be honest, one of the things I always get tripped up on with QFT is fields.
Fields, yeah.
Like, what are they? Are they like those force fields in like Star Trek or something?
I wish that would be awesome. But yeah, it's a question that always comes up, and it takes a little bit of like a mental shift. Got to kind of rewire your brain a little bit to think about it. Forget those like little billiard ball particles you learned about in, basic physics. In QFT, those particles, they're really disturbances. They're like, excitations, of these underlying fields.
Excitations.
Yeah. Like imagine a calm pond, right? The surface of the water, that's your field.
Oh, okay.
Now, toss a pebble in, the ripples that spread out, those are like your particles.
Ah, okay. So the field is like the canvas and the particles are like the paint strokes on top of it or something.
That's a great way to put it, yeah. So like the electromagnetic field, it's all around us, right? But we only actually see it
Yeah.
when there's a disturbance, a photon, which we see as light.
Okay. Yeah, that makes a little more
Okay.
sense. And, while we're talking about things that are a little mind-bending,
Yeah.
What about this quantization thing I keep hearing about? What does it mean for something to be, like, quantized?
So think of it like climbing a staircase.
Yep.
In the quantum world, energy levels, momentum, spin, all that stuff, it's not like a smooth ramp. It's like you can only step on specific steps. You can't have half a step.
Yeah.
That's quantization.
Yeah.
These things come in like discrete packets.
No in between.
No in between. You're either on one step or the next.
Wild. And what about these creation and annihilation operators? Are those like magic wands that make particles appear and disappear?
They kind of sound like magic, right? But they're actually really powerful mathematical tools that we use in QFT. And they help us describe this crazy idea, right? That particles can just like pop in and out of existence within these fields.
So they're blinking in and out of existence.
Yeah, exactly. It's like they're blinking on and off, and these operators help us understand how that happens.
And why? Okay, you've been talking about all this incredible stuff, and I think we got to address the elephant in the room, which is the math.
Ah, the math.
Yeah, because you're talking about these complex ideas, and I'm sure there's some serious math behind it all.
There's a good amount of math, but,
Should be worried.
don't worry, we're not going to
I'm
dive
so-
deep into equations here. But, the math is important, right? It's like our toolkit. It helps us actually, work with these ideas.
Okay.
So we've got things like the Lagrangian and Hamiltonian formalisms. These are ways to figure out how fields and particles evolve over time. And then you have Feynman's path, integral formulation. That's a whole other way to calculate probabilities.
So it's like having different lenses to view this microscopic world. Right?
Exactly. Different tools for different jobs.
Okay. But I've heard that early QFT calculations, they ran into a bit of a problem. Something about infinities.
Ah, yes. the infamous infinities. It was a real headache, you know? Some of these early calculations, they're spitting out infinite results, which...
That doesn't really work in the real world, does it?
No, not really. Infinity doesn't quite fit on a lab bench, right?
Exactly. So how did they, get around that?
That's where renormalization comes in. And it's a pretty brilliant technique. It's basically a way to, systematically remove those infinities and get meaningful results that we can actually test.
So they tamed the infinities.
Yeah. They found a way to, make sense of the infinities.
Okay. Well, that's good. Because infinity, I don't think I could wrap my head around that.
Yeah, that's a tough one.
Okay, now, I keep hearing this term, gauge symmetry. And I gotta be honest, it sounds kind of intimidating.
Gauge symmetry, yeah. It might sound complicated, but at its heart, it's actually pretty elegant. It's all about, these internal symmetries within fields. And the really cool part is that gauge symmetries, they give us this framework to understand the fundamental forces of the universe.
Wait, so forces are connected to symmetry?
Exactly. It's one of the beautiful things that comes out of QFT.
Okay, I did not see that coming.
Yeah. And we've got, these really good examples, right? We've got quantum electrodynamics, or QED. That's the theory of how light and matter interact.
Got it.
And then you've got quantum chromodynamics, or QCD, and that describes the strong force, which is the force that binds quarks together inside protons and neutrons.
Okay, so QFT is not just about particles and fields. It's also, the language of forces.
It's the language of how the universe works, yeah. It's pretty amazing.
Okay, this is blowing my mind. But it gets even better, right?
It does get even better.
Because, you were talking about these symmetries, right? And then there are these conservation laws. Are those related somehow?
Absolutely. So these symmetries in QFT, they directly lead to these fundamental conservation laws that you might remember from, physics class, conservation of energy, momentum, electric charge, all of that.
So it's all connected.
It's all connected, yeah. And there's this powerful mathematical statement called Noether's theorem. And it beautifully links these symmetries to the conserved quantities.
It's like the universe is dancing, right? Everything's moving together in this beautiful harmony. Particles, fields, forces, conservation laws.
It's all one big cosmic dance.
That's incredible. And I feel like we're building up to something even bigger here, right?
We are building up to something big. We're building up to the standard model of particle physics. So everything we've been talking about, the fields, the quantization, the forces, the symmetries, they all come together in this model. It's the best theory we have to explain most of the particles and forces in the universe.
The standard model is like the blueprint of the universe, right?
Yeah.
And what about the Higgs boson? Where does that fit in?
Oh, the Higgs. That's a great example, right? So the Higgs boson, it was predicted by the standard model. And when they actually found it, huge triumph for QFT.
Yeah, that was big news. It was like finding the missing piece of the puzzle.
Yeah. And it just shows how powerful this whole framework really is.
So QFT is like the foundation for how we understand everything at the subatomic level.
Pretty much.
But even with this super successful model, there are still some mysteries out there, right?
Yeah, there are definitely some big mysteries left. Take dark matter and dark energy.
Oh, yeah, the invisible stuff.
The invisible stuff. We know it's out there, but the standard model doesn't tell us what it is.
And what about neutrinos?
Neutrinos, those are tricky little particles. They seem to break all the rules. Their masses are still a big mystery.
Okay, so are physicists just giving up at this point?
Oh, no way. They're coming up with some pretty wild ideas to try and figure all this stuff out.
Like what?
Well, there's supersymmetry, for one.
Yeah.
The idea that every known particle has a hidden superpartner. And then there's string theory, where the universe is made up of these tiny vibrating strings.
Okay, that sounds like next level stuff.
Yeah, these are some of the big ideas that physicists are exploring right now, trying to push beyond the standard model.
It must be hard to, test some of these theories.
It's incredibly challenging. I mean, imagine trying to build a particle collider the size of the solar system. But that's the beauty of science, right? We keep asking questions.
Yeah, we never stop exploring.
We never stop exploring, and that's what makes it so exciting.
Okay, so just to recap, QFT, powerful framework, help us understand the universe. But the journey is far from over, right?
Yeah, we've learned a lot, but there's still so much more to discover.
And that's what keeps it interesting. So to all you listeners out there, if you're feeling inspired to dive even deeper into this wild world of QFT, don't hold back. There's a whole universe waiting to be explored.
Absolutely. There's always something new to learn.
All right. Well, on that note, until next time, keep on exploring.